Welcome back to the deep dive. You guys have really outdone yourselves this time, giving us a whole bunch of physics notes and textbook excerpts.
Oh, yeah?
Yeah, and it's all about electricity, but specifically static charges and fields.
Huh, cool.
Yeah, so get ready because we're going to
Yeah.
explore the forces that make our world.
The forces, literally.
It's going to be pretty awesome, I think. I think it'll be fascinating to connect those everyday zaps we get from static,
Oh, from static electricity?
yeah, to like Coulomb's law
Oh.
and Gauss's law, some pretty powerful physics concepts.
Exactly. I've always wondered about those static shocks.
Yeah.
The zap you get from your clothes, the crackling sounds when you peel us a sweater,
Oh, yeah.
or even lightning. What's actually going on at
Uh,
like a fundamental level when we experience those things?
Well, it all comes down to electric charge, this fundamental property of matter.
Okay.
Just tiny little electrons are leaping between surfaces, just seeking balance.
Oh, interesting. And in that process, you get those sparks and sounds that we think of when we think about static electricity.
So those everyday experiences are actually giving us clues about this invisible world of electric charges.
Yeah, that's right.
That's pretty cool.
Uh-huh.
And speaking of history,
Yeah.
our sources mention that even the ancient Greeks
Yeah.
had some insights into this, right?
Absolutely. Around 600 BC,
Okay.
there was a Greek philosopher named Thales of Miletus.
Thales of Miletus.
He observed that amber, after being rubbed, would attract, like, light objects.
Interesting.
And that's actually where we get the word electricity, from the
Oh.
Greek word for amber, electrons.
So the name for this fundamental force
Yeah,
is rooted in these ancient observations.
it is.
It makes you wonder
Yeah,
what other simple observations from the past could unlock
Totally.
future scientific breakthroughs,
yeah,
But getting back to those charged objects,
yeah.
what did those early experiments with like rubbing materials together reveal
Yeah.
about how charges actually behave?
Those experiments were really key in establishing, like, the fundamental nature of charge.
Okay.
So they showed that charge isn't something we create. It's just an intrinsic property of matter.
Okay.
When we rub materials together, like a glass rod and silk, we're really just redistributing the charges that are already there.
Gotcha.
And a key principle came out of that, like charges repel each other
Oh.
and opposite charges attract.
Oh, it was like a tiny dance floor?
Yeah,
And everybody's just looking for their opposite to pair up with.
exactly.
But then our notes mentioned conductors and insulators. What role do they play in this?
Yeah, that's a great point. So conductors, like metals,
Okay.
they allow charges to flow easily.
Okay.
And insulators, like glass or plastic,
Oh.
they resist that flow.
So that's why if you
Exactly.
get a shock touching a doorknob
Exactly.
after watching on
Yeah.
carpet,
Yeah.
you become a conductor.
You become a temporary conductor.
All that shuffling around
Right.
builds up charge.
Yeah.
And when you touch that metal doorknob,
You get a path to ground.
all those charges have a pathway.
Uh-huh.
That makes a lot of sense. It's like you're creating a pathway
Yeah.
for those charges to escape.
Exactly.
Our source mentions a tool called a gold leaf electroscope.
Oh, yeah.
It uses that principle
It does.
to detect the presence of charge visually.
Yeah. It's a simple but very elegant way to show that those invisible forces are at play.
Okay, so to really understand what's happening,
Yeah.
we need to go deeper into those fundamental building blocks
We do.
of charge itself.
We do.
Okay, so let's dive in.
Okay.
Our notes mention that charge is quantized.
Uh-huh.
What does that mean?
Think about it this way. You can't have half an electron, right?
Okay.
So charge always comes in these like fundamental units, which we call E.
Okay.
And these units are carried by protons, which have a positive charge, and
Okay.
electrons have a negative charge.
Okay.
And this quantization of charge
Yeah.
is key to understanding how electricity works at like the atomic level.
So it's like the currency of the electrical world.
Yeah,
It always comes in specific denominations.
That's right. And just to give you a sense of the scale here,
Mhm.
even though charge seems continuous, like at our level, right, or macroscopic
Right.
level,
Oh, right.
it's actually made up of these teeny tiny discrete units.
Okay.
So it's like, those grains of sand on the beach?
Oh, yeah.
At a distance, it looks smooth and continuous, but up close, you can see the individual grains.
That's a great way to think about it.
Yeah.
And our source material had some pretty mind-blowing examples
Oh, yeah.
to illustrate how many of these charges are present,
Yeah.
even in just ordinary objects.
Yeah.
Like, it would take a surprisingly long time
Uh-huh.
to get 1 Coulomb of charge
Yeah.
just from the flow of electrons.
Yeah.
And a Coulomb
The
is...
standard unit of charge.
Okay.
Yeah. It's a lot of charge.
And then there was this example of, like,
Yeah.
calculating the positive and negative charge
Mm-hmm.
in just a cup of water.
Oh, right.
It turns out that it's enormous.
It is huge.
So even though matter is usually
Electrically neutral. Overall, it contains just a massive amount of positive and negative charges.
at the atomic level,
Yeah.
okay, so we have these charges.
Yeah.
But how do they actually interact with each other?
Yeah.
What makes them attract
Yeah.
or repel?
That's where Coulomb's law comes in.
Okay.
It's kind of like the gravity of the electrical world.
Okay.
So it describes the force between 2-point charges.
So is it kind of like gravity, where the force depends on the masses of objects
Yeah.
and the distance between them?
It does have some similarities.
Okay.
So Coulomb's law says the force between two charges is proportional to the product of the charges. And just like gravity depends on the product of masses. So bigger charges means stronger force.
Okay, that makes sense.
Yeah.
So does distance play a role too?
Absolutely. Just like with gravity, the electric force is inversely proportional to the square of the distance between the charges.
Okay.
So if you double the distance,
Uh-huh.
the force becomes 4 times weaker.
So the closer they are,
Yeah.
the stronger the attraction or repulsion.
The stronger the force.
Our source mentioned that Coulomb used this device
Yeah.
called a torsion balance to figure all this out.
It was a very clever way to measure those really tiny forces between charged objects.
So the electric force is way stronger than gravity.
It is
Much stronger.
orders of magnitude stronger.
Wow, so these tiny particles
Yeah.
are exerting these forces far greater than what
Yeah.
we might think based on our everyday experience with gravity.
Our source highlights this by comparing the electron-proton attraction to the proton-proton repulsion.
Okay.
So the electric force is just, it totally dwarfs the gravitational force between them.
Incredible. So even though we don't always see these forces,
Right.
they're at work
They are, yeah.
all around us, shaping how matter behaves at like the most basic level.
At the most fundamental level.
But what happens when we have more than two charges?
Yeah.
Does it get more complicated?
It can seem pretty daunting, but thankfully there's this principle that really helps to simplify things.
Okay, what is it?
Superposition.
Superposition.
Yeah.
Okay, so what is superposition?
Okay, so superposition tells us that when you have multiple charges, right, you can just add up the individual forces from each charge to find the net force on a particular charge.
Okay.
So it's almost like each charge is just ignoring the others.
Okay.
And we just add up like their contributions.
So we break down a complex problem into smaller pieces?
Yeah, exactly.
And our source material had some visuals.
Oh, yeah.
Like vector addition diagrams
Right.
to help explain this?
Yeah, so like arrows representing the magnitude and direction of each force.
Yeah. And then we just add them up like following directions on a map.
Exactly.
But what if the arrangement of these charges isn't so straightforward? Our source mentioned a scenario with 3 charges at the vertices of an equilateral triangle.
Oh, okay.
And I'm imagining those force vectors
Yeah.
pointing in all sorts of directions.
This is a great example to consider.
Yeah.
And what's really interesting is that the net force at the center of that triangle is 0.
Really?
Yeah.
So could you explain why that symmetry is so important?
Yeah, so the symmetry in the equilateral triangle example means that the forces from the 3 charges perfectly balance each other out.
At the center?
At the center, yeah. So it's like a tug of war with 3 equally strong teams pulling in different directions.
And nobody wins.
And nobody wins. But if we disrupt that symmetry, say, by making one of the charges negative, then those forces won't cancel out so perfectly.
So symmetry is key in determining that net force.
Yeah.
Okay, but that also highlights a challenge. How do we actually map out these invisible forces?
Yeah, good question.
Between the charges.
Yeah, that leads us to one of the most powerful concepts in electrostatics.
Yeah.
The electric field.
Okay, so what is an electric field?
Okay, an electric field is like an invisible map of the force that a positive test charge would experience at any point in space.
Okay.
So think of it this way. Even when there are no other charges present, right? The field from like a source charge, it still exists. It's just waiting to act.
So it's like a potential force field.
It is.
Surrounding every charge. That's pretty mind-blowing.
Yeah, it's kind of wild.
And what's important to understand here is that the field lets us separate the source of the force.
Yes.
So the charge creating the field from what experiences the force.
Right.
The charge that feels that force.
Yeah.
They don't have to be in direct contact
Exactly.
for that force to be felt.
They don't.
Our source uses this analogy.
Yeah.
Imagine an electron falling in a uniform electric field.
Oh, okay.
Like gravity, but for charges.
I like that.
So the field acts on the electron, causing it to accelerate.
Exactly.
But how do we actually visualize these fields?
Yeah, well, they are invisible.
Yeah.
But thankfully, we have this awesome tool to help us see them.
Okay.
Field lines.
Field lines.
Yes.
Okay.
They were invented by Michael Faraday.
Oh, cool.
As a way to represent those electric fields graphically.
So they're like signposts.
Yeah.
In this invisible landscape of forces.
I like that analogy a lot.
How do they actually work?
Well, the density of the field lines, so how close together they are, represents the strength of the field.
Okay.
So closer together, stronger field. Yeah. And the direction of the lines shows the direction of the force on a positive test charge.
So if the field lines are pointing away from a charge, that means a positive test charge would be repelled.
Exactly.
That makes sense.
Yeah.
And our source material has some good diagrams.
Oh, does it?
Showing these field lines for simple charge configurations, like a single point charge or a dipole.
Okay,
which is
two opposite charges.
Two opposite charges.
Yeah.
Okay.
So those diagrams really help us visualize how the field lines spread out from positive charges and converge toward negative charges.
So we're starting to map out this invisible world
we are,
of electric fields.
That's right.
But I'm curious, are there any rules or principles that govern these field lines? Are they just random squiggles?
They're not random, no.
Okay.
There is an order to them.
Yeah.
So there are some key properties that govern field lines.
Okay.
And one of the most important, they never cross.
Never cross.
Nope.
Why not? What would it mean if they did cross?
Well, if field lines crossed, it would mean that at that point of intersection, the force on a positive test charge would have two different directions.
Oh, okay.
And that's not physically possible.
Gotcha.
So field lines, they always got to flow smoothly and continuously, never intersecting.
So we're building this understanding of charges, forces, and fields.
Yeah.
But how do we actually measure the strength of an electric field? Is there a way to quantify how much of this invisible force is flowing through a certain area?
Yeah. So that's where the concept of electric flux comes in.
Okay, electric flux, what is that?
Okay, so electric flux. It's basically a measure of how much electric field is passing through a surface.
Okay.
Think of it like a water hose spraying on a window.
Okay.
More water flows through if the window is like directly facing the spray, right?
Right, that makes sense. So if the window's tilted, less water gets through.
Exactly.
Okay.
Same idea here. The amount of electric flux depends on the strength of the field and the orientation of the surface.
So if a surface is perpendicular to the field lines, we get maximum flux.
Yeah.
And if it's tilted, it decreases.
Exactly.
Okay.
Yeah.
But how do we connect this idea of flux back to the charges themselves?
That's where things get super elegant.
Okay. Why?
We have this really powerful tool called Gauss's law.
Gauss's law.
Yeah, that directly links electric flux to the charges enclosed within a surface.
Okay, so Gauss's law. Tell me more. It sounds like a game changer.
It is. So Gauss's law basically tells us that the total electric flux through a closed surface is proportional to the charge inside that surface.
So if we can measure the flux, we know how much charge is there.
Yeah.
Even if we can't see it.
That's right.
That's amazing.
It is.
And it works a little way, too.
It does, yeah.
If we know the charge inside, we can calculate the electric field.
You got it.
Okay, I'm seeing how elegant this is. But I'm a visual learner, so could you walk me through some examples of how we actually use Gauss's law?
Yeah, absolutely.
Our notes mention a few classic cases.
Oh, okay. Let's start with the infinitely long charged wire.
Okay.
So imagine a wire stretching out forever in both directions.
All right.
With a uniform charge along its length.
Okay, I'm picturing it.
All right, you could.
So how do we even apply Gauss's law to something that's infinite?
Well, the trick is to choose a really smart Gaussian surface.
Gaussian surface.
Yeah, it's like an imaginary surface that encloses the charge that we want to analyze.
Okay.
In this case, because the wire is symmetrical, the best choice is a cylinder.
Okay, a cylinder.
Around the wire.
Yeah, that makes sense.
Yeah.
It matches the symmetry of the wire.
Exactly.
But why is symmetry so important here?
Well, the symmetry makes sure that the electric field is constant and always perpendicular to the cylinder surface.
Gotcha.
And this really helps us calculate the flux through the cylinder easily.
The symmetry helps us avoid complicated math.
That's right.
So what does Gauss's law tell us about the electric field around this infinite wire?
So it tells us that the field strength
Okay.
is proportional to the linear charge density of the wire.
Linear charge density.
Yeah, so it's basically how much charge is packed along each unit length.
Gotcha.
And it's inversely proportional to the distance from the wire.
So the farther away you are, the weaker the field gets.
Exactly. It's kind of like a ripple spreading out from the wire, getting weaker as it goes.
Okay, so from this complex situation,
Yeah.
we get this simple relationship
We do, yeah.
between field strength, charge density, and distance.
That's right.
Okay, that's pretty cool. What's next?
Okay, so the next example is an infinite charge plane.
An infinite plane.
Yeah, so picture a flat sheet that's infinitely large, and it carries a uniform charge
across its whole surface.
Yeah, so we need to choose a Gaussian surface again to take advantage of that symmetry.
I'm thinking a box shape with two faces parallel to the plane.
Exactly. That's perfect.
Okay, cool.
And because the electric field from an infinite plane is uniform and perpendicular to the plane, the flux only goes through those two faces.
So the other sides of the box, it's zero.
It's zero, yeah.
Okay.
And using Gauss's law here, we get a kind of surprising result.
Okay, what is it?
The electric field is constant.
Constant.
Yeah.
So it doesn't matter how far away I am.
It doesn't, no.
From the sheet?
Nope.
The field strength's the same.
It is, yeah.
It's like this endless wall of electric force.
Yeah, that's a great way to think about it.
So even though these are like abstract infinite cases, they give us real insight into how fields work.
They do, yeah. They're really useful.
Okay, I'm seeing that.
Yeah.
We're building this like understanding.
Yeah, we're building that foundation.
That we can use in more realistic situations.
Absolutely.
So what's the last Gauss's law example?
Okay, so the grand finale is a uniformly charged spherical shell.
Okay, a spherical shell.
Yeah.
What's that?
So imagine a thin hollow sphere with charge spread evenly over its surface.
Okay.
And we want to know what the electric field is like, both outside and inside.
Okay, so starting outside,
I
have a feeling this might connect to something we talked about earlier.
You're on the right track.
Okay.
So outside the shell, the electric field acts like all the charge is at the center.
So it's just like a point charge?
Exactly.
That simplifies things?
It does.
Okay, what about inside the shell?
This is where it gets really cool. So inside the shell, the field is zero.
Zero. But there's charge all around.
I know. It's weird.
On the surface.
I know. It seems counterintuitive, but Gauss's law explains why.
Okay.
So if we imagine a Gaussian surface inside the shell, there's no charge in there, right?
Right, because it's all on the surface.
Exactly.
Okay.
And because the flux through that surface has to be zero, the only way that's possible is if the field is zero.
So even though I'm surrounded by charge, there's no force inside it.
That's right.
Wow, that's really hard to wrap my head around.
I know. It's pretty wild.
So this idea of zero field inside a charged shell, it's not just theoretical?
It's not, no. It's been proven experimentally.
So it gives more evidence for Coulomb's law.
Yeah, exactly.
So all these laws, they're all connected.
They are, yeah.
Supporting each other.
It's pretty amazing.
That's incredible. And our source mentions that this uniformly charged sphere idea was used in an early model of the atom.
Right, it was, yeah.
So that model helped to visualize how the field changes as we move from outside the atom, where it acts like a point charge, to inside, where it goes to zero at the nucleus.
It's a simplified model, but it's still helpful.
It's fascinating how these ideas connect, like the big world we experience to the tiny world of atoms.
Yeah.
What happens when the charge distributions aren't perfectly symmetrical?
Oh, good question.
Our examples have been pretty ideal.
Yeah, so in those situations, things can be a bit trickier. We often have to use like direct integration with Coulomb's law.
So no more shortcuts with Gauss's law?
Not always, no.
Okay.
It's still a fundamental principle. But using it might need some more complex calculations.
Okay.
It's like the difference between using a map with clear landmarks versus going through a dense forest.
Sometimes we have those landmarks of symmetry.
That's a great analogy.
To help us.
Yeah, I like that.
And sometimes we need to like rely on our math skills to find our way.
Exactly.
But even in those tough situations, the basic principles still apply.
They do.
That's the beauty of physics.
It is.
It gives us a way to understand the world from simple interactions to complex phenomena.
That's right.
But we've covered a lot.
We have.
Maybe we should recap.
Yeah, good idea.
For our listener.
Yeah.
Before we go on to our next adventure.
Absolutely. Let's give everyone a minute to digest all this.
Yeah, all this amazing knowledge.
Yeah.
All right. I think we've given our listener a good foundation in electrostatics.
Yeah, I think so.
We've talked about charges and forces and fields and even Gauss's law.
We covered a lot.
Yeah, we really did. But there's still a few things in static electricity that I want to explore.
Okay, cool.
You mentioned before that even objects that are neutral can experience electric forces.
They can.
And I thought only opposite charges attract each other.
Right.
So how does that work?
That's a great question.
Yeah.
So it's all about this thing called polarization.
Polarization.
Yeah. So even though a neutral object has equal positive and negative charge, right?
Right. Overall.
Yeah. Overall,
yeah,
those charges can actually rearrange themselves.
Oh, interesting.
In response to an electric field.
So even if the object starts out neutral, the field can cause the charges to shift around within the object.
Inside,
creating these regions of positive and negative charge.
That's right.
So they're not evenly distributed anymore.
Exactly. It's like they're doing a little dance. Trying to line up with that external field.
That's a great way to picture it.
Yeah.
So that's how a charged comb can attract little pieces of paper.
Yeah, exactly.
Even though the paper's not charged.
Yeah. So the comb's field polarizes the paper. Inducing a little charge separation. So the side of the paper closer to the comb becomes a little bit negative, and the farther side a little bit positive.
And then there's that attraction between the comb's positive charge and the negative charge on the paper.
That's right.
That's strong enough to overcome the repulsion from the positive side of the paper.
That's a great way to put it.
Wow, that's amazing. So even neutral objects can play a role.
They can.
In this electric force interaction.
Yeah.
Because of polarization.
Exactly. And polarization is more than just like a theory.
Oh, really?
Yeah, it's super important in physics and chemistry. It influences how molecules behave and materials, even biological systems.
It's really fundamental.
It is, yeah.
You've given me a whole new appreciation for those simple static electricity things we see every day.
It's pretty amazing stuff, right?
From static cling to polarization, we've uncovered this world of invisible forces that are at work all the time.
All around us.
Yeah, all around us.
Shaping our reality.
It's pretty incredible.
It's been great diving into this with you.
Yeah, it really has. And it's remarkable how these basic concepts, like electric charge, they underpin so much of our understanding of nature.
They really do.
And this is just the beginning.
That's right.
We talked about static charges.
Yeah.
But our sources suggest things get even cooler.
Oh, yeah.
When we start thinking about moving charges.
Oh, I like where this is going.
Yeah, that's where magnetism comes in.
Right.
And how electricity and magnetism are connected.
That's right. A whole new world to explore.
I can't wait. But for now, I think we've given our listeners a lot to think about.
I think so, too.
To our listener, thanks for joining us.
Yeah, thanks for listening.
On this electrifying journey through electrostatics.
Yeah.
And we hope you've learned something new.
And maybe spark some curiosity.
And until next time, keep exploring, keep asking questions.
And never stop learning.
Exactly.